So hello everyone, welcome to the next lecture. Today we are going to cover Compton effect. So Compton effect confirms the photon model further, and it actually works on conservation of energy and momentum. So now when you focus quantum theory of light, it says that photon behaves as a particle except that it does not have any rest mass. Like every particle do have some kind of rest mass, but photon is exception to that point. So the question arises, can we make a collision of a particle which do not have any kind of rest mass? For example, with electron, can we collide photon? The answer is yes, and the same effect is known as Compton effect. So this is the schematic here, that a incident photon is there, and it is actually incident on a target electron. So for incident photon, you can have energy that is h nu, and momentum is h nu upon c, and energy of the target electron is actually mc square, and momentum is 0 as it is on rest. So when it collides, there will be scattering. Electron will scattered in a different direction, and photon will get scattered in different direction. And this whole effect is known as Compton effect, and it is important because a wave nature, or a kind of thing which has mainly wave manifestation, is actually trying to interact with a particle. Okay, or in other language, you can say that a particle which does not have any rest mass is actually colliding with a particle that has rest mass. So obviously whenever two things collide, so energy and momentum is the basic conservation principle which is going to hold true, and as a result a scattered photon will have less energy than the incident photon, because that incident photon will share the uh, energy with the target electron. So when you apply the conservation of energy principle, so you know that energy of incident photon is h nu, and energy of electron which is at rest is mc square, and then say that energy of a scattered photon is h nu prime. Okay, so this nu prime is actually with nu prime the changed frequency of photon, and the energy of a scattered electron is actually pc square plus mc square whole under root. Okay, this is the formula from relativity. In relativity, you know that formula is given actually by E square is equal to P square C square plus E naught square, and this E naught is actually mc square. Okay, or many people also write it m naught c square. So applying conservation of energy principle, you know that whatever there will be loss in photon energy, the same energy will be gained in the electron. So when you apply conservation of momentum principle, so you know that initial momentum in x direction should be equal to final momentum in x direction. So initial momentum in x direction of the whole system will be h nu upon c for photon, and this 0 is for electron. Now it changes to h nu upon c cos phi plus p cos theta. So you know that from this schematic here. Okay, because theta is the angle of scattering of electron, and phi is angle of scattering of photon. So the mathematics is very simple. Now we apply the same conservation principle for momentum in y direction. So in y direction there was no motion, so it is 0 initially, and finally it is going to be h nu prime by c sin phi minus p sin theta. You know clearly here that angle between direction of initial photon to the direction of a scattered photon is given by psi, and angle between direction of initial photon to the direction of a scattered electron is given by theta. Now when you rewrite the momentum equation, you will simply get pc cos theta is equal to h nu minus h nu prime cos phi, and pc sin theta is equal to h nu prime sin phi. So now when you square the above equations and add them, so term including theta will get eliminated, because you know cos square theta plus sin square theta is going to be 1. You will simply get P square, C square, and on the right hand side you will get H nu whole square minus 2 H nu into H nu prime cos phi plus H nu whole square. So now we have two fundamental equations from relativity. The first is energy is equal to kinetic energy plus rest mass energy, and energy square is equal to P square C square plus rest mass energy का whole square. So when you use the equation A and equation B together, you simply get this equation where P square C square is equal to K square plus 2 m C square K, where K is nothing but kinetic energy. Now we know that kinetic energy is actually the loss of energy of photon, so we could simply relate that initial energy of photon is h nu. It is initial energy and h nu prime is final energy. So we know that this is the loss of energy in photon, and same is going to be the kinetic energy of electron. And this is pretty simple from energy conservation law. So using the value of kinetic energy from equation 7 into equation 6, we could simply get this expression. Okay. And when you compare equation 5a and 8, you simply get the final expression after so much manipulation, that is lambda prime minus lambda is equal to h by mc into 1 minus cos phi. So what is lambda prime here? So lambda prime, we know that primed quantity is the quantity associated with photon after the scattering, and the unprimed quantity is before the scattering. So this whole equation expresses the Compton effect, where a photon is interacting with matter and it is losing its energy, and that loss of energy or change in energy is actually denoted by the change in wavelength or change in frequency. So this equation actually gives change in wavelength, and when photon undergoes a scattering after collision with electron, this is what we get, and we simply know it as Compton effect. And this whole quantity, that is h upon mc, where m is mass of electron, is known as Compton wavelength, and when you calculate it, it is going to be a constant, which is 2.426 picometer. So this is what is Compton effect, and I'm not going to focus much on the simple mathematics. We are just going to focus that what we are doing. So we are, for example, I'm going to tell you that we are using value of kinetic energy from equation 7 into equation 6. So this is equation 7. Okay, and now you know that where equation 6 is, so this is equation 6. So this is a simple trick I am going to tell you, and the mathematics are very basic. Mathematics we are going to cover by on, and you just know need to remember the end result, that is lambda prime minus lambda is equal to h by mc multiplied by 1 minus cos phi, and phi is nothing but the scattering angle of, look here, photon to the incident direction. So till now we are done. Now we will move towards the particle duality, which is going to be a very important lesson for us. So let us meet in the next. So hello again, we are going to cover a very important part, that is wave particle duality. So we know that wave and particle, they have dual nature. That means sometime a particle may seem to be like a wave, and sometime a wave could be like a particle. So they share their property. How? We will see it. So I'm sorry for me coughing. So let us start with the wave properties of particle. A moving body behaves as if it has wave nature. A photon of light frequency nu has the momentum, that is h nu upon c or h by lambda, and it is actually from this relativistic formula. It is very important formula. One must remember it, that is E square is equal to P square C square plus m naught C square to the whole square. This is actually nothing but rest mass energy. Okay, so in this way you will get the photon wavelength to be h by p, where h is nothing but Planck's constant and p is momentum, and it is in relativistic form it is gamma mb, where gamma is nothing but relativistic factor, which is given by 1 divided by 1 minus v square upon c square whole under root. So this was the simple thing, okay? And this whole formula is also known as de Broglie hypothesis. Okay, we will see it. De Broglie hypothesis. It was later confirmed by Davison and Germer experiment. De Broglie hypothesis confirmed by Davison and Germer experiment. And this has been PYQ actually. Previous year question में ये पूछा गया है. This has been asked in previous year question in UPSC. So now we have some solved questions. So like so that a neutron beam can show diffraction, interference phenomena like X-ray. So a neutron beam, if they are showing diffraction and interference phenomena, that means they are particles. And diffraction and interference are actually properties of wave. So if they are really showing such a thing, then we could say that wave particle duality is something which is true, which is visible in nature. So we know that kinetic energy of neutron at room temperature is going to be kT. You could directly find it from the formula in thermal physics, kinematics. Okay. So associated de Broglie wavelength is h by p, where p is momentum and momentum is actually under root 2me. Okay, in this way, when you put the value of E, that is kT, so you will get h divided by under root 2m kT. When you put all the value, you will get the wavelength to be 1.77 angstrom. So as we can see that de Broglie wavelength associated with thermal neutron is in order of interatomic distance. Hence, neutron beam can show the diffraction and interference phenomena. Because we all know that to show diffraction and interference phenomena, the wavelength should be in the order of interatomic distance. Wavelength should be in order of interatomic distances. Okay. Now the next question is, so that de Broglie phase velocity exceeds the velocity of light. Okay, so this is the very classic question. So we all know that de Broglie wave velocity to be written as Vp, and mathematically we may rewrite it as Vp is equal to frequency multiplied by wavelength. Okay, frequency times wavelength, that is the phase velocity, and wavelength of such de Broglie wave is actually lambda is equal to h by p, which is equal to h by gamma mb, where we know that gamma is nothing but relativistic factor, that is 1 divided by 1 minus b square by c square. Okay. Now what we are going to do, we are going to equate the quantum expression of energy. That energy have the classical expression and energy have the quantum expression as well, that is energy is h multiplied by frequency of the wave, with total with the relativistic total energy formula, that is energy is equal to uh, gamma mc square, and where gamma is nothing but the relativistic factor. So when we do that, we get this expression for frequency, which is equal to gamma mc square by h. We have denoted the same thing with equation 2. Now when we substitute this equation 2 in equation 1, we get actually c square by v. Okay, so Vp is equal to c square by v. Okay, you can do it mathematically. Pause the video, substitute this value of frequency into this value. You will directly get Vp divided by Vp is equal to c square divided by v. Okay, and from here we could simply sense that Vp is greater than C. Okay, because it is C square and it is just V, so B is not going to be more than C. So obviously Vp is going to be more than C. That is the mathematical analogy, because we know that B could never be greater than C. Now the next thing we are going to do is, what voltage must be applied to an electron microscope to produce electrons of wavelength 0.40 angstrom? So we are directly going to use again the same formula, that is lambda is equal to h by p, and where p is momentum and momentum is nothing but it is 2 times m times kinetic energy, that is root 2 me. Okay, and energy is actually charge multiplied by voltage, that is E is equal to charge multiplied by voltage, and charge is here E and V is voltage, so energy is EV. So with such a thing you can get the voltage formula pretty easily just by using your calculator. Now the next formula, next equation is, you have 10 electron volt photon and 10 electron volt electron. Which one has shorter wavelength? It is very simple. Okay, when you find the wavelength, it is actually going to give you, for photon, the only important thing is that for photon, you are going to use the relativistic formula given by E square is equal to P square plus C square plus M naught MC square by whole square. It is M naught actually. So what you will do, for in the case of photon, the momentum is actually energy divided by C. Okay, how? So it is very simple. Let me explain you. This is the parent equation. E square is equal to P square C square plus M naught C square whole square. Okay, so for photon this quantity is 0, so we simply get E square is equal to P square C square. So from here you get P is equal to E by C. So when you calculate the wavelength of photon, it is going to be 124 nanometer, and when you repeat the same process, that is h by p is the wavelength of electron, and here p is momentum, and for the electron, because electron is a kind of which do have actually rest mass, so we are simply going to use the formula of momentum as root 2 me. Okay, so when you substitute the values, you simply get 3.88 angstrom. So what could be the interpretation of the result? So depending on momentum, de Broglie wavelength differs. Okay, if the momentum is going to change, obviously the wavelength is also going to change, because the basic formula is that wavelength is actually h divided by momentum. Okay, and also the photon and electron are a different kind of entity. Electron is a kind of particle which have rest mass, and photon don't have rest mass. Now let us move to the next question. Find the wavelength associated with de Broglie wave with an electron having energy 1 million electron volt. So we know that, we simply know that the rest mass of an electron is 511 kilo electron volt, or 0.511 million electron volt, which is less than the given energy in the question. That means our case is relativistic case, and momentum should be formulated in a different way. If the case is going to be non-relativistic, note it down, it is very important. For non-relativistic case, momentum is actually 2 times m times kinetic energy and whole under root. But in this case, as the case is relativistic, because our given energy is more than the rest mass energy. Okay, so from relativity we will have again two forms of energy. One is energy is equal to kinetic energy plus rest mass energy. This is rest mass energy, and this is kinetic energy. And another is energy square is equal to P square C square plus rest mass energy whole square. So when we use both the formula to get the momentum, we get momentum actually as kinetic energy multiplied by kinetic energy plus 2 m naught C square, then whole under root divided by C. So we use the same formula, so we get Hc divided by this, and when you substitute all the value in the definite form, we get lambda to be 8.739 multiplied with 10 to the power minus 13 meter. So this is the wavelength. Now we have another question that an alpha particle accelerated through a potential difference of 2000 volts. So what is the wavelength of the associated de Broglie wave? So again, it is being accelerated, the alpha particle. So we need to have to know the momentum, and for momentum we need to know the energy, that is kinetic energy. In such case, we know that energy gained is actually charge multiplied by voltage. So charge is 2A and voltage is 2000 volt. So with this thing, you can directly get the wavelength, which is going to be 0.2272 angstrom. Now we know that we cannot waste time in calculation part, so we are just using the common sense that for mass we need to have 4 times mass of proton, because that is the case for alpha particle, and charge of alpha particle is 2 times charge of electron. Okay. So now let us move to the next part. We need to find the glancing angle at which electrons of 100 electron volt should fall on the lattice planes of a crystal to obtain a strong Bragg's reflection in the first order. So what we need to do, that electron of 100 electron volt means electron has kinetic energy of 100 electron volt. Thus we need to find the corresponding de Broglie wavelength. And let me tell you again, this is not called de Broglie, but it is pronounced as de Broglie. So de Broglie wavelength would be h by p, and p is nothing but 2 times m times e whole under root, and when you substitute all the required values which is given in the question, okay, so you are directly going to get lambda to be 1.226 angstrom. Now coming to the glancing angle for the first order Bragg's reflection, n is going to be 1, and 2d sine theta is actually Bragg's diffraction law. We will also learn it in solid state physics. We will also learn it in Davison and Germer experiment. Davison and Germer experiment. So when I substitute all the value, we get the glancing angle in the form of sine theta, and theta is nothing but around 16.56 degree, and obviously we know that in UPSC we are allowed to use the scientific calculator. So use your calculator to find all the values. Now let us solve the next question. So there is a beam of monoenergetic neutrons which corresponds to 27 degrees centigrade. Let me tell you, the something which corresponds to some temperature, the energy is actually k times t, where k is Boltzmann constant. So such monoenergetic neutrons are actually allowed to fall on a crystal. So a first order means in the Bragg's reflection law you need to put n is equal to 1. So a first order reflection is observed at a glancing angle of 30. So we have theta is equal to 30 degree. So you need to calculate the interplanar spacing of the crystal, that is d. So we know that there is the formula 2d sine theta is equal to n lambda, and the thing is very simple. For n barabar 1, we are going to get 2d sine 30 is equal to lambda, and lambda is nothing but h by p, and p is nothing but h divided by 2 times e whole under root, and we know that e is nothing but kt, 2m kt whole under root, and this is actually 2d sine theta. So from here we can immediately find the value of d by putting all the values. In this way, when you put all the values, we get d equal to 1.78 angstrom, which is the interplanar spacing. This is the whole thing. Okay. So now let us move to the next part. A 0.83 electron volt neutron scatters from unknown sample, and a Bragg reflection peak is observed around 22 degree. The angle is given, okay, and that is the reflection peak at around 22 degree. So what is the spacing of Bragg's plane? So again we need to find the wavelength of the wave, because we have the formula for the Bragg's reflection, 2d sine theta is equal to n lambda. So lambda, that is wavelength, we should know. So wavelength is nothing but 0.993 angstrom. Okay. And for the reflection peak, let us consider the first order reflection, that is n is equal to 1. Okay, so 2d sine theta is going to be lambda, and d is simply lambda divided by 2 sine theta. When you substitute all the value, you get d to be 1.33 angstrom. So that is the spacing of the Bragg's plane. Now, it is again the same question, so you may solve it at your own. So now let us move to the next part. It is again on the same topic, that is Bragg's diffraction law. Now, we are here we are going to solve something different, and yeah, so let us start it. So find the de Broglie wavelength of 50 kilo electron volt electron and 50 kilo electron volt proton, and compare the amount of diffraction of these particles in the first order by crystal with the grating space of 9.5 angstrom. Here a grating space or interplanar spacing, it is also called as interplanar spacing. So this is the given energy. So energy given is comparable to the rest mass energy of the electron and proton. So we could count it as relativistic case. So de Broglie wavelength will be actually h by p, and p is given by this expression, that is under root kinetic energy multiplied by the sum of kinetic energy and 2 mc square. So when you substitute all the values, and let me tell you again that hc is actually 1240 electron volt nanometer. So this is the ready-made result, you should remember. Okay, and whenever you substitute all the value, you get the wavelength for electron to be 5.37 multiplied by 10 to the power minus 12 meter. So to calculate the amount of diffraction, that is you need to calculate the theta. So 2d sine theta is actually n times lambda I, and n is going to be 1 because it is first order diffraction. So in that way, when you calculate theta E, that is theta for electron, it is going to be 0.16 degree. And when you do the same mathematics for 50 kilo electron volt proton, you get here theta proton to be 0.004 degree. So electron suffered more diffraction than proton. That is the final result. Now we are going to solve P by Q. So find the de Broglie wavelength associated with electron of energy 10 electron volt and 10 million electron volt. Okay, so there is a whole lot difference. So 10 electron volt is very less than rest mass energy. So we could consider it non-relativistic case. So momentum will be simply under root 2m e. And when you substitute, it is going to be momentum is h by p, and when you multiply h by p with c and c, we get hc divided by under root 2 m naught c square e. And I'm calling it m naught c square because it is the way it is. Most book actually uses, so m naught c square is rest mass energy. So rest mass energy for electron is well known, that is 0.511 million electron volt. Okay, it is the ready-made answer. So when you substitute such value, you get actually lambda to be 3.88 angstrom. And when you repeat the same thing for 10 million electron volt, the only difference will be the expression for PC, that is this. This is the relativistic expression. So you know that P is simply 2me under root in if the case is not relativistic. And for relativistic case, P is given by kinetic energy multiplied by kinetic energy plus 2 times m naught c square whole under root divided by c. So this is the relativistic case. Okay, so that is the two different expression for momentum we do use. Now we have next question, that is another another PYQ. So the momentum of an electron is 600 kilo electron volt per speed of light. Okay, so that is actually the way to notice write the momentum expression in the term of c, that is speed of light. So we need to determine its de Broglie wavelength, phase and group velocity. So de Broglie wavelength is pretty simple. Okay, lambda is h by p and momentum is given 600 kilo electron volt divided by C. So you can directly calculate it to go towards 2.066 multiplied by 10 to the power minus 12 meter. Now for phase velocity, the expression is omega by k, and when you multiply omega by k with h bar both in numerator and denominator, you actually get E by P. And now you have expression for energy in relativistic form, that is P square C square plus mc square whole square under root. And let me tell you again, whenever I write this mc square, it invariably means the rest mass, that is m naught. Okay. So P square C square is going to be 600 kilo electron volt whole square, and this is the rest mass energy, that is 511 kilo electron volt. So when we calculate the whole thing, we get the phase velocity to be 1.31 times speed of light. So this is actually more than speed of light. That is the way it is to be. And for group velocity, the formula is d omega by dk. Okay. And when you multiply h bar again in both numerator and denominator, it is going to be dE by dP. So we need to find dE by dP from this expression. So we differentiate both the sides. So it is going to be 2E dE is equal to C square 2P dP. So the dE by dP is going to be C square P by E. So when you substitute the values for C square P divided by E, we actually get 0.761 C. Okay. And let me tell you, for verification, whenever we multiplied by phase velocity to group velocity, you will actually get C square. So you can do it, you will get it. Now we have another previous year question. So a 200 electron volt increase in the energy of an electron changes its de Broglie wavelength by a factor of 2. So this is very important phrase here, that whenever there is 200 electron volt increase in the energy of an electron, its de Broglie wavelength is changing by a factor of 2. So we know that whenever you are increasing the energy of an electron, the de Broglie wavelength will actually decrease. So it has decreased by a factor of 2. How do we know that it is decreasing? So know that lambda is actually h by p, and it is going to be h by 2me. Whenever energy is going to increase, obviously wavelength is going to be decreased because they are inversely related. So we need to calculate the initial wavelength. So we know that de Broglie wavelength is inversely proportional to energy. So suppose initial wavelength is lambda, so then lambda is going to be h by p, and it is again then going to be h divided by root under 2me. So now when you increase the wavelength, energy by 200 electron volt, wavelength is going to change by a factor of 2. That is, you divide it by 2 because it is going to decrease. So to decrease it, you will have to divide it. If the question was to increase it, it would have been multiplied. So that is the meaning of factor. So in this way, lambda by 2 is going to be this expression, because we are increasing the energy, so wavelength is automatically going to decrease. And now when you are going to solve the equation 1 and equation 2, you will simply get energy to be 200 divided by 3 electron volt. And we may also use energy to get lambda. Okay, because once we have energy, we could easily get lambda by using the de Broglie hypothesis. Okay, so put it in this formula, and simply we will calculate that it is going to be 1.502 angstrom, because 10 to the power minus 10 meter is 1 angstrom. Now let us calculate the wavelength of de Broglie waves associated with electrons accelerated through a potential difference of 200 volt. Let me tell you, if electron is being accelerated, the energy it will gain is charge multiplied by voltage. So here the same thing, energy is QV. So in this way we know that energy is QV. So now we are using this formula, and we are multiplying it by C in both numerator and denominator to make our calculation easy, because we have the ready-made value of Hc, that is 1240 electron volt nanometer, and here C when comes under root, it is going to come as C square. So mc square is actually rest mass energy of electron, that is 511 kilo electron volt, or 511 million electron volt. Okay, so now we have everything. So whenever you solve it, you actually get lambda to be 8.67 multiplied by 10 to the power minus 11 meters. So this is the whole way to solve things. Okay, now we are required to calculate the de Broglie wavelength of neutron at 20 degrees centigrade. So we know that total energy possessed by neutron is 3 by 2 kT, or you can use kT as well. KT is going to be more accurate depending on what kind of velocity you are using. Okay, from the kinetic theory, I mean the average velocity or probable velocity. So as per me, kT is going to be more accurate, and it is not going to create much difference because the order is going to be same. Like 1 kT or 1.5 kT is not going to create much difference in the order of the energy. So energy is going to be around 0.037 electron volt, and wavelength used is actually h by p, which is equal to h divided by root 2 me. Okay, and when you do the same thing, that is calculation, you can get 1.486 angstrom. So now we will do 25 and 26 later on, and because that this question belongs to different exercises. So let us conclude now. We will meet in the next